Hey everyone, welcome back. Today we're doing day 20, bubble sorting. And for this task, we'll be discussing a simple sorting algorithm called bubble sort. So before we talk about bubble sort, let's quickly understand the question. For this task, we're given an array A of size n, and we have to sort this array of integers in ascending order using the bubble sort algorithm above. So HackerRank gave us an implementation of bubble sorting, but we'll be getting to that in a bit. So once we sort this array with bubble sort, we'll be printing three things. The first is the number of swaps that we use in the bubble sort, and the second and third is just the first element and the last element of the sorted algorithm. So in short, for this task, we'll be needing to implement bubble sort and edit it so that it returns the number of swaps that happen in the bubble sort algorithm as well. So before we can tackle this problem, let's quickly go through how bubble sort works. So bubble sort is one of the simplest sorting algorithms available. And how it works is that it performs a number of linear scans, maximum up to the number of items that exist in the list. So let's say, for example, you have a list of 5 numbers, like this. In this case, the maximum number of linear scans that you'll be performing through this list is up to 5. But it is possible to terminate this bubble sorting algorithm if the array is already sorted in place at any time after every iteration of bubble sort. So let's keep track of the number of iterations that we have. And in every iteration of bubble sort, we'll be keeping track of this pointer. Let's call this J. And J will start off from the leftmost side of your bubble sorting algorithm. And this J, for the first iteration, will iterate from index 0 to index 3. And I'll be explaining in a bit why is it that we iterate it from 0 to 3 instead of all the way to the end. At every single position of J, what we do is that we compare its value together with its neighbor and check whether if J is currently larger than its neighbor. And if that's the case, we would swap them. So the idea behind using J as an iterator is to swap numbers such that the larger element is swapped towards the right. So notice that in this case, after the first position of J, we swapped 4 and 5. The number of swaps that we have just done is 1. Let's move J towards index 1, and now we compare 5 with 2. Now 5 is larger than 2, so we swap them. And now we have 2 swaps that's happening. Now we compare 5 with 1 and notice that J is indeed larger than 1. So in this case, we swap them. And we move J to the final position for the first iteration. Compare J together with its neighbor, and we see that J is larger, so we will swap them again as well. Notice in this case, we do not move J to the final element here, because if we do that, there is no neighbor on the right to compare. So for the first iteration, we will always move J from the first position, index 0, all the way to the second last position, index 3 in this case. And notice that in this case, we have performed 3 swaps for this first iteration. So notice that after the first iteration, the largest element in the array is guaranteed to be on the right side of the array. In other words, 5 is already sorted in place, and what this means is that in the second iteration, there is no need for you to compare 5 with J in any case. So what this means is that for the second iteration, J will iterate from index 0 to index 2 instead, because the neighbor that we'll be comparing is up to 3, so that's pretty much it. So now we move on to the second iteration, and now let me introduce another iteration swap counter as well. This iteration swap indicates the number of swaps that we have occurred in every iteration, and I'll be showing how this can be used to optimize the bubble sort algorithm. So now we compare J with 2. We notice that J is larger than 2, so we swap them. Now we have 1 iteration swaps. We increase the number of swaps that we want to return back, and we move J here. Now 4 is indeed larger than its neighbor, so we swap them again, increase the swaps, increase the iteration swaps that happen in this iteration, and we move it move on j to the final position for this iteration, which is index 2. Now j is still larger than its neighbor, so we will swap them. And notice in this case, we are done with iteration 2. Now we have 6 swaps, and now we have 3 swaps in this iteration. So now, since we know that we have 3 iteration swaps for this current iteration, it hints that the array is not sorted yet. So we will move on to iteration 3. And at this point, notice that after the second iteration, 2 elements on the right are now sorted in place. Both of them, 4 and 5, are guaranteed to be already sorted. So for iteration 3, we'll only be moving j from index 0 to index 1. So now we move j back to index 0, and now we reset the iteration swap to 0, and now we compare. So j is still larger than its neighbor, so we will swap them. Now there's 1 iteration swap there. We increase the number of swaps, and we move this pointer here again and compare j with its neighbor. 2 is smaller than 3, so we leave it be. So in this case, notice that after iteration 3, the 3 elements to the right of your array is guaranteed to be swapped. So now we're done with iteration 3. Let's go to iteration 4. We set iteration swap counter, and now for this final iteration, we can see that we only need to compare j for this position. So there is no swaps. J is indeed smaller than its neighbor, so there's no swaps. And now there is no iteration swaps, and we terminate. And at this point, because we know that there is no iteration swaps, we will just terminate it because the number of swaps is equal to 0. And indeed, we can terminate because if you look at this array is already sorted in place. So that was quite a mouthful, but I hope that this was clear on how the bubble sorting algorithm works. So in a sense, bubble sorting works by performing linear scans across the whole array, and we keep track of one pointer j. And what we do with this j is that we will just compare j with its neighbor, and we will just bubble the larger number towards the right. And we will continue to do that until after one iteration, the rightmost element is guaranteed to be the largest element. We are pretty much bubbling the largest element towards the right of the array on every iteration. So that is why for a list of size 5, we need up to 4 iterations to bubble every large element towards the right. So after 4 iterations, 4 elements will be sorted in place, and by elimination, the final element will be sorted in place as well. So that's pretty much how bubble sorting works. Now that we are sure how bubble sort works, we can finally implement it ourselves and also edit it to keep track of the number of swaps to be returned back to HackerRank. So with that, let's get started. The first thing I will do is import the type hint list, because we'll be using this a lot to give type hints for better readability. Line 17n refers to the number of elements that is inside the list of integers. So this is really an integer. And for line 19, this is the past list of integers that is meant to be sorted. So now we're ready to start implementing our bubble sort algorithm. So to do that, I'll be implementing a bubble sort algorithm that takes in an input list. And this algorithm will be returning a copy of input list that is sorted along with the number of swaps taken for bubble sort. So this would return back a tuple. The first element of the tuple will be the sorted list itself. The second element will be the number of swaps that was used to perform this swap. So now we're done. Let's define a copy sorted list of integers, and let's assign this to input list, but make a copy of it. If you do not use this copy method, which makes a shallow copy of the input list, if you try to edit sorted list, it will edit the input list in place. So we do not want that. So because of that, we make a copy of this input list instead. The benefit is that by any chance, if you want the unsorted list, you can use this algorithm and it will not make any edits to the input list. So this way you will still have the old copy as well as the new copy. The only drawback is that you'll be using an additional block of memory to keep track of this new sorted array, but that's fine for this case. So now the first thing to implement is the iteration across the whole sorted list. So for iteration in range length of input list, let's define this convenience variable n that refers to the length of the input list. And as we saw just now, if you have a list of 5, we will take up to 4 iterations. So in this case, it's really n minus 1. So if your list is of size 5, then we will take up to 4 iterations to sort this list. So the next thing that we'll define is j, which is the pointer that we discussed just now. And the range will be from 0 to, let's say, n minus iteration minus 1. So in this case, for the first iteration, it will iterate from 0 to n minus 1. So if 5 is the length of the list, then we will iterate to index 3. So notice that if iteration is 0, then we will iterate to 0 to 4. And because 4 is exclusive, we'll be iterating from index 0 to index 3. So this makes sense. So now we are ready to start making the comparison. So for every position of j, we compare it with its neighbor. So if sorted list j is larger than sorted list j plus 1, then we will do a swap on this sorted list, and we will pass in the 2 indexes that we want to swap, which is j and j plus 1. We will implement swap in a bit. And on top of that, we will also keep track of the number of swaps, total number of swaps. And we will be incrementing this by 1. Another thing that we will do is also define iteration swaps. This will be for optimizing the bubble sort algorithm. We will terminate if there is no swaps happening. And that means that the array is already sorted in place. So with that, that's pretty much it. Once we're done, we can return the sorted list together with the total number of swaps. Now the last thing that we have to do is define swap, the method for swapping and a list of integers. So this swap algorithm swaps 2 positions in the list in place. So actually, yeah, there's no need to return that list actually. So the first element would be list, input list. This will be a list of integers, the left index to swap as well as the right index to swap. So to do that, we can just do input list left, input list right equals to input list right, input list left. And that's pretty much the implementation of swapping. Another alternative is to use a temp variable to keep track of the input list on the left. You could assign input list right to left to input list right, and input list right to temp. You could implement it like this as well, that's totally fine. It's just that in Python, you could do this syntactical trick. So there's no need for you to define a temporary variable yourself to keep track of the left element before you assign the right element to the left element and the right element to the temporary one. There's no need for that. You can just do it in one line like this in Python. So once we're done with this bubble sorting algorithm, we can try it out. So we can say sorted A. Let's get sorted A together with the number of swaps that we take. And let's pass in the bubble sort list here. And with that, we can start printing out this syntax over this expected output over here. So number of swaps. The next one is the first element of the array. This would be sorted A 0, as well as last element, which is the last element of this sorted A. So this would be sorted A minus 1. And just like that, we are done. Let's run this against some test cases. Okay, this passed, and let's run this against more test cases. And there we go. And before we end this, let's just check whether if A was in, by any chance, if there was a bug such that A was actually edited. So to check that, I'm going to print out A before and after the sorting algorithm. And as you can see, the array was indeed not sorted. Let's give it an unsorted array just to see that A was not sorted. So yeah, looks great. So with that, that's pretty much it for this demonstration. I hope that this video was clear on how bubble sort works, and I hope that this gives you more confidence and more clarity in how you should implement optimized bubble sort in Python. And with that, that's all for this video. If you find this useful, please give us a like and subscribe, and we will see you in the next video.